first thanks Professor Ian Stewart and other course staff for this great EFTX course. And my talk is about effective field theory of inflation, and I will mostly follow this original. Let me first review some introductory background about inflation. As we know, standard hot Big Bang cosmology has some problems like horizon problem or flatness problem that to solve it we extend time to a period called inflation, which has one remarkable property, and that is the Hubble radius, which is inverse of AH, should be decreasing. This property can be characterized by a parameter called epsilon, which measures changes of the Hubble parameter by minus h dot over h square, and so it should be less than 1. In the case where epsilon is completely zero, is correspond to a perfect de Sitter space. But if epsilon be small, then it can be interpreted as a semi-de Sitter space. Also, to solve those problems that I mentioned, we need that the condition of smallness of epsilon holds for sufficient amount of time, and then it can be characterized by another parameter called eta, which measures the fractional change of epsilon per Hubble time, and it should be much less than 1. Then, for realize these two conditions, the most simple model is a single field slow roll inflation, where we use a scalar field called phi, the inflaton, which is minimally coupled to gravity through this action. Now we can go to a gauge called unitary gauge, where the fluctuations of the inflaton is 0, and so all the perturbations is due to metric perturbations. The special part of the metric perturbation is written here, and the perturbation parameter zeta is called curvature perturbation, because when we look at the phi equal constant slice, we see that when we compute the extrinsic curvature on this slice, it becomes related to the square of zeta. Then due to this fact, we call it a curvature perturbation. But this curvature perturbation has one remarkable property, and that on super horizon scales it should be constant. Look at this graph. As I said, inflation is a period of increasing Hubble radius, and then after reheating, the Hubble radius should increase. So this is the period of what we call super horizon scales, where the wavelengths of the modes is greater than the Hubble radius, and we said that during this period zeta is constant. And it is important for us because when we do experiments on CMB, because this zeta is constant to the super horizon scales, then we can get information about correlation function of zeta at horizon crossing by doing experiments on CMB 2 days. The correlation function of zeta first have a delta function, which is not, which is just what is expected from translation invariance. It is delta function of momentum, and then another dependence on k, which we call it power spectrum. The form of power spectrum is 1 over k cube times a constant. This constant is h squared over 4 epsilon, and this form of 1 over k cube is due to a scale invariance. It is generally conventional in the cosmological literature to, instead of talking with p zeta, talk with a dimensionless quantity called delta s square, which is k proportional to k cube times p zeta, and mm, uh, which at horizon crossing is we can say that it is h squared over h pi squared times epsilon. As I say, this dependence of 1 over k cube is just due to a scale invariance. But if the theory is not completely a scale invariance, then there is a parameter called ns minus 1, which measures the deviation from the scale invariance. So ns minus 1 is equal the derivative with respect to logarithm of k of logarithm of del s square. As I say, inflation is a period of semi-de Sitter period, but we know that it should be end, and so there should be a physical clock that that realizes this end of inflation. Then this physical clock would give us a privileged spatial slicing that we can choose the slicing so that it coincides with the with constant time surfaces, so that delta phi be 0. This is what I already mentioned. This is the unitary gauge under which in which the inflaton perturbation is 0, and we only should consider the metric perturbations. So in this gauge, our Lagrangian should be generally invariant under spatial diffeomorphism, that is when xi goes to xi plus kci. Now the only parameters that we can add to our Lagrangian are the scalar, the Ricci scalar, the G00, which is also invariant under the time under the spatial diffeomorphism, and also another parameter k mu nu, which is extrinsic curvature of those spatial of those constant spatial of those constant surfaces. So we can write our most general Lagrangian by this. This is the usual Einstein-Hilbert action. Here is our two linear terms, and then 1 plus G00, because G00 of the background is minus 1, then it should be equal to delta G00, which is the quadratic imperturbation. Here is cubic imperturbation. But we can also add the extrinsic curvatures to this. Here I neglected them, and this is because this action would be dominated by the least number of derivatives. And what I mean, if you consider d mu by energy, and you know that d mu is proportional to energy over lambda, then we know that in the cosmological scale we deal with energies of order h, the Hubble parameter, and so this expansion is a perturbation of parameter h over lambda. Then we can look at these two linear terms, and there are the only two terms that contribute to variation of action with respect to metric at zero order, which, as we know from GR, is proportional to T mu nu. And we are interested in FRW background, so the T mu nu is fixed by FRW equation. And so if we solve those equations, we can find the parameters C and lambda in terms of Hubble parameters. And this is just what is called tadpole cancellations. Then we can substitute the parameters C and lambda in terms of H from those two earlier equations to our actions, which then the action would be like this. If we consider the linear terms and then put all the other higher order terms coefficients 0, we can see that by using Friedman equation, mp times h dot is equal minus phi dot square over half over 2, and then mp 2 times 3h square plus h dot is equal the potential of a slow roll inflation. And so if we use this in M of action, we find our usual single field slow roll action in unitary gauge that in general can be written in this form. But what is interesting is that we can also see more general cases. For example, if the R Lagrangian be a function of d phi square and phi, in the unitary gauge it would be function of g00 times phi dot square and phi. And in this case, so they would have contributions from other nonlinear terms. And this is, for example, what we expected from dBi inflation, which has some contributions from M2 and M3. We know that breaking the gauge symmetry corresponds to describing additional degree of freedom. That means if we do gauge transformations that break the symmetry, we should introduce a new degree of freedom to make the theory gauge invariance. So if I want to remind you, I want to give an example from gauge theory. For example, look at this Lagrangian with this mass term that mu, we know that it's not invariant under the gauge transformation. So what we can do is to introduce a Goldstone boson pi, which then this term then become a mu minus d mu pi square, such that pi transform to pi minus lambda, and then we find that now this theory become gauge invariance. If we want to apply this procedure to our case, firstly for simplicity, let us look at our Lagrangian and only include the linear terms in it. Here, we know that these terms, as I said, they are not invariant under the time diffeomorphism, that is t goes to t plus kc0. And we want to see that how this Lagrangian transform under this diffeomorphism. So we should look at the transformation of the g00, which would be like this. And then we can substitute this transform the form of the metric in our previous action, which would look in this form. And now we can describe this action in terms of tilde variables and kc0 that then we can come to this action. And now, as our example in gauge theory, we can introduce the Goldstone boson to kc0 be minus pi, and so the M of action, which is action of our Goldstone boson actions, become like this. Then if we impose that pi goes to pi minus Kc0, then this action would be invariant under all diffeomorphism. Then we have a theorem called the Goldstone boson equivalence theorems that implies that physics of Goldstone bosons decouple from metric fluctuations at high energies. So we can apply our procedure to our general Lagrangian and then we get this form for our general Lagrangian. But what is important here is to check that in what energy scales the Goldstone bosons become decoupled from metric, and so we are allowed to use the Goldstone boson action over that energies. For doing this, we should compare the kinetic terms and the terms that mixing with metric. Here, in leading order of the kinetic term would be proportional to mp square h dot pi dot square, and the mixing term would be proportional, would be equal to mp square h dot pi dot delta g00. And the delta G00 is just the gravitational potential which is determined by pi, and so we know that mp square h dot di times di delta G00 can be approximated by h dot mp square di pi, and so we can approximate delta G00 by h dot over h times pi. And then, so this ratio of mixing to kinetic term, which is equal delta G00 over pi dot, by using this approximation become equal h dot times pi over h times pi dot. But also we know that the derivative with respect to time is proportional to energy, so we can read it e times pi, and so it will become this ratio simplified to h dot over eh. And the fact that we want this ratio be much less than 1, so that we can so that the Goldstone bosons become decoupled from the metric fluctuations, is that h dot over eh should be much less than 1. And the absolute value of this h dot over h is what we called earlier epsilon, and so the regimes where we can look on Goldstone boson's action is on energies which is much greater than epsilon h, which is called E-mixing. So we can apply our procedure that we said earlier to our general action, which we can introduce zeta 0 equal Kc0 equal minus pi, and introduce pi so that pi transform to pi minus Kc0, and then our general action in terms of Goldstone boson would like this. But here what is important is that the pi gauge is not a good gauge to look at for to its correlation functions, because as I said, what is constant over super horizon scales is the zeta function. So we should transfer from pi to zeta, And it can be done, we can set pi equal 0 by doing a time diffeomorphism such that delta t become equal minus pi, and then in this way the spatial part of the metric become like this. And on this, then we can find that a relationship between zeta and pi, so that zeta equal minus h times pi. And so we find that the correlation function of zeta is just h squared times correlation function of pi. Also, we should pay attention that these pi's should be canonically normalized. So these are the canonically normalized pi. And now by looking at Lagrangians in terms of pi, we see that in our kinetic terms, the time derivatives and the spatial derivatives have different components, and it is leads to the fact that the speed of sound that is Cs is not equal to 1. So these are those two coefficients that I said. And first, pay attention that because we don't want to get instabilities, these coefficients should be greater than 0. And then the speed of sound is defined as the ratio of these two terms. And so we find that how higher dimensional operator affects the speed of sound through this equation. And also we are interested in the cases where h dot is less than 1, h dot is less than 0. And so if we want to Cs not become greater than 1, we should impose that m2 should be m2 to the 4 should be greater than 0. And now we can solve this equation for m2 in terms of Cs. And then substitute the amount of m2 in our original action. Then our original action become this. So from now, by introducing this speed of sound, we see that p zeta have a correction of 1 over Cs. And to have an intuition that where does this 1 over Cs comes from, we should check that p zeta has 1 over kq, and here we should rescale k to Cs times k. But also we have a kinetic terms as here, such that so this kinetic term introduce a new Cs square factor, and so the 1 over Cs cube should cancel by Cs squared, and then it becomes 1 over Cs. Also, in this case that we have a small amount of speed of sound, we can write the ns in this form. But a small amount of speed of sound would lead to long interactions, and it is what we call non-Gaussianities. So to estimate the size of these non-Gaussianities, we should compare the nonlinear terms, which here in leading order is proportional to pi dot times delta pi square. We can also check that if we compute the pi dot cube, it has a less contribution to this, so we don't discuss it here. But so we should check the ratio of the nonlinear terms here, pi dot times delta pi square, with respect to quadratic ones. And here we have pi dot, which the derivative with time is proportional to energy, and in our scales it would be h times pi. And here is a special derivative, but a special derivative is proportional to energy over Cs, and so in our energy scales it becomes h over Cs, and when we simplify it, it becomes h times pi over Cs square. And the the h times pi is just, we call it, it was zeta, and so this ratio becomes zeta over Cs square. But it is more conventional in the cosmological literatures to give these scales in terms of FNL, and so it becomes FNL times zeta. And so in this case we find that FNL is something proportional to 1 over Cs square, which is something of order 100. And so we find that we can use this to give how these ratios of higher dimensional operators should be. For the last remark, pay attention that these descriptions in terms of effective action is true until the strong couplings. So we should find that what is this strong couplings, and to do so we write our Lagrangian for another times, but here we rescale the pi to the canonical pi's in this way, and then here our coefficient m star would become this. And so we expect that the theory become strongly coupled at energies like m star to the 4. But here there is one subtlety, and this is that our theory here is non-relativistic. Our speed of sound can be small, and so we should check the dimensionality of this. By dimensional analysis, we see that m star to the 4 is equal k to the 7 times omega 2 minus 3. And then it lets that lambda star to the 4 become m star to the 4 times Cs to the 7. So this would be the correct form of lambda star to the 4. And so if we substitute in the above, this Cs to the 7 cancelled with this Cs square, and so our strong coupling scale become mp square dot cs to 5 over 1 minus cs2. And we see that for a small amount of speed of sound, cs much less than 1, this would be suppressed, and we want that our energy scales, that is our scale of the Hubble scale, should be much less than these strong coupling scales. If we put a small amount of speed of sound, then the h to the 4 should be much less than mp square h dot times cs to the 5, and then it leads that cs should be greater than fourth root of the p zeta, which by experimental data is of order 3000s. So if we want that we want to have a small amount of speed of sound, and our theory, energy scale of theory, become much less than a strong coupling scale, we need that CS should greater than 3000s. Okay, this is my talk, and thank you for your attention.